Hi, everyone, and welcome to our webinar on Building for the Future, Integrating Fire Resilience with Energy Efficiency in High Performance Design. We're excited to have you all join us today. This webinar is being hosted by the New Buildings Institute. We're a nonprofit think tank focused on a wide range of national and regional policy programs and technical initiatives focused on energy performance, carbon reduction, and climate resilience and adaptation in the built environment. All of our work is directed towards the aim of making buildings better for people and for the environment. This webinar is also funded by the San Diego Learn program, a workforce education and training program that has partnered with NBI to offer free energy efficiency and electrification webinars. You can learn more at sandiegolearn.com. So a quick overview of our program today. The climate continues to change, and we are seeing wildfires ignite at increasing frequencies and severities in places like the Western United States. These tragedies have called those of us in the design, development, policy, engineering, consulting, and other professional communities to address the urgent need for building solutions that not only withstand the threats of wildfires, but also address their root cause, which is climate change, through sustainable, energy efficient, and carbon efficient design. Our panel discussion today will be focused on fire resistant building strategies and their alignment with climate mitigation strategies. As you will see from the great lineup of presentations during this hour, there are many approaches that exist today that mutually fulfill both of these elements and also offer a range of other benefits like occupant and community health and environmental well-being. So as I mentioned, we have a really fantastic lineup of presenters today. A quick introduction to them. Cameron Chorney is an associate and senior engineer with RDH Architects, leading the development of RDH's Southern California practice. He's experienced in both new building projects as well as building enclosure assessments and renewals of existing buildings across the country. He specializes in high performance building design, including net zero construction, wildfire resistant enclosures, climate resilient enclosure design, and the development of policies and guidelines to advance building science. Ali Keenan is an architect and designer who founded her own boutique practice, Ali Keenan Architecture. Her work responds to site and climate, celebrates the craft and honesty of materials, and has a sense of place and locality. She is a healthy material and sustainability advocate while actively researching alternative building methods and fire-resistant practices with the goal of making architecture more accessible and affordable for all. And finally, Ben Loescher is the founding principal at Loescher Meacham Architects, where his work focuses on the reuse of existing buildings, high-performance workplace design for the film, television, and media industries, and innovation in earthen construction. In 2009, he created Adobe Is Not Software, the firm's advocacy arm that informs, enables, and advances Adobe construction in California. Ben was the chair of the Earth Builders Guild, the U.S. Trade Association for Earthing Construction, from 2016 to 2023, and is a board member of Adobe in Action, a New Mexico-based nonprofit focused on assisting individuals in creating affordable earthen housing. So before we begin with this excellent panel, we wanted to start off with a quick quiz. Just to get you all kind of engaged in thinking about this issue. So the question is, based on your awareness of the recent LA wildfires, which may have been informed by news coverage or the ensuing conversation afterwards, what physical elements in the city do you think contributed the most to the spread of the Eaton fire? Was it trees and landscaping, homes and cars, or lighting, communications, and energy infrastructure? So take a second to fill this out, and then we'll discuss the results. So like maybe we'll close it now. Great. Wow. Um, a perfect tie between trees and landscaping and homes and cars. The correct answer was homes and cars. And while kind of a poll by its very nature kind of simplifies the story, and there are many variables at play in over the course of a wildfire event, there was kind of a common sentiment that emerged from these wildfires that trees and landscaping were the largest culprit of the spread of the fires, which has led to conversations about landscape removal to prevent future fire spread. But what we saw in the context of the Eaton fire was kind of through observation of the area post-disaster that urban trees and plants were not the primary culprits. It really was homes as well as cars as the most combustible parts of the cityscape that really fueled the spread. An observation of the area after the disaster found that many trees, shrubs, and even lawns survived, and trees that were found burned tended to be surrounded by homes and cars. Um, so this is one reason why buildings are the focus of our webinar today. As a significant contributor to the problem, they can also be a significant part of the solution. So I'll stop my introduction now with just a bit of housekeeping, which is that we'll leave some time at the end for discussion and Q&A. So if you have any questions for the panelists that arise during the presentations, please feel free to submit them in the Q&A box. And also this webinar and slides will be recorded and posted online so that you can watch this back in the future. So with that, I'll stop my share and turn it over to Cameron for his presentation.
Great, thanks, Ariel. And I assume everyone can see my screen there. Seeing some nods, great. Yeah, so like Ariel mentioned, Cameron Chorney with RDH Building Science. We're consulting engineers focused on building enclosures. And as you'll see today, it has a large contributing factor to wildfire performance of homes and other buildings. Quick disclaimer, trying to push out some information in industry and providing concepts here. So project by project definitely can change. And what I'll talk about today is mostly what is wildfire resistant construction, why do we need it, get into some nitty-gritty assemblies and details that we can hopefully use on similar projects, and then look to the future and the current state of how do we minimize future events moving forward. So why wildfire resistant construction? Yeah, so not every structure is susceptible to wildfire, and you can kind of see the triangle of wildfire risk that we simplify here. So on the left, it's likelihood. Is there going to be a wildfire where you're at? Intensity, talking about will structures catch on fire or just trees maybe. And then finally, susceptibility. So looking at, is your building susceptible to that wildfire if and when it does occur? So you really need all three sides of the triangle to be in a risk situation. And I'll mention WUI or wildland urban interface throughout this presentation. So just quick definition for you. Geographical area identified as a fire hazard severity zone or other areas as designated by the enforcing agency to be at significant risk from wildfire. And this is a picture from Lahaina, which we know what happened there, unfortunately. And you can see the brushland on the right, and then right next to a community there. So that's ideal definition. picture format. And in terms of who is in that zone, the WUI zone, in reality, it's about 3% of the U.S. population, and so that's 1 in 6 Americans live in a significant wildfire risk beyond being in that. So it's closer than a lot of us think, unfortunately. And how might you know that you're in this WUI zone or wildfire risk? So a lot of it is defined in building codes, and from the building codes, they look to the local, fire marshal. Here in California, the wildfire maps that identify on a map where there is various levels of fire risk and severity, and that helps inform your decision making or need to be wildfire resistant. So Ariel mentioned kind of trees versus cars versus homes at the start, and these WUI fires and disasters progress in various ways, but more often than not, it starts with a fire starting. Maybe it's a spark from a electrical wire, maybe it's some other ignition source, and with some high winds or dry conditions, that spreads in the wildland. And then when getting to the interface zone with houses, a lot of times it's ember transport that causes a lot of these homes to start igniting. And from there, we go from a wildfire, WUI zone fire to a structure or residential fire, which has a lot higher fuel density and load. And accordingly, you can see the consequence on the lower side. So a brush fire, single brush fire, pretty easy sometimes for firefighters to get to. But then we start progressing to more fires and then more structure fires. Firefighting resources can become overwhelmed pretty quick, and that's when it gets to a larger scale event like we saw, unfortunately. So I mentioned how fires start. So Ara mentioned the cars and homes versus trees and bushes. So that the initial transport or start of a lot of the structure fires starts when the fire is away from homes, and it's actually the embers from various trees that are burning in high winds that get blown towards structures and get into ventilated soffits and to combustible materials in our structures that then catch on fire and then can progress to the structure fire type thing. A lesson learned from the Camp Fire in 2018. So we can see these numbers. Homes built before 2008, 18% survived, and homes built after 2008, maybe 51 or more percent survived. So what happened there here in California? That was when Chapter 7A in the California Building Code came into effect. Implementing wildfire resistant construction. So proof in the numbers that it can work, and we do know how to help make it work. But still, then even code minimum, there is still some risk there, as we see with just 51% surviving. And here's a visualization of the embers. You can kind of see them floating through the air there. So high winds, those can be transported up to a mile or more, based on some studies and testing. And then you might see on the news, these homes that one survives and everything else around it is devastated. And some might say it's it's magic or they got so lucky. But if you look at this home on the bottom, it has a zone around it that is non-combustible and probably non-combustible construction, wildfire resistant construction. So it is possible, and it does work. So from there, how do we build those homes or those structures? And really, wildfire resistant structure is intended to reduce obviously that structure ignition due to wildfire, and then based on that slows the spread throughout the community. So we'll talk a lot about the structure today, but Ara mentioned the big aspect is the landscaping and limiting the fuel in close proximity to your structure. So think the first 5 or 10 feet around your home with limited or no combustible material for those embers to catch on fire, and then more fuel load. And then outside of that, looking more to community level, limiting maybe the trees, or having certain wildfire resistant type trees and foliage to help limit that risk. And then finally, wildfire resistant construction is not fireproof per se, but it's meant to resist the loads that we're seeing with wildfire. And then for maybe some architects in the room, you might hear a fire resistance rating. A lot of the times we're thinking about interior and exterior when you might hear that in the code. So similar concept for exterior to interior with wildfire. So we'll say fire resistant rating quite a bit. And a nice kind of example, a lot of different assemblies can be fire resistant. Even a straw bowl with stucco assembly here, there's some testing to show that it is wildfire resistant. And then looking at the various things that put together our structure that we need to think about. So you can see all the various aspects that we'll look at. So starting with the roof, we'll say non-combustible or fire resistant exterior surface a lot, and that's Class A roofing in this example. All flashing pipes, vents. Like I mentioned, the embers are a big one with ventilated roof assemblies. So having vents that won't melt, so they're non-combustible, and that don't allow embers to go through them into that attic space, which has a lot of combustible materials up there, is super important. And then gutters, having a screen that stops debris from your trees from getting in there, more fuel essentially. Using soffits, so you can see kind of bottom right with exposed wood, which is a high risk and very, very likely to catch on fire in a wildfire event. And then on the left, we saw some soffit venting, but they're not non-combustible. They fell out, and that can cause fire. So being non-combustible is important. And then we're talking, looking at mitigation, and solar panels are a big aspect of mitigation efforts in our building codes. So they, also have fire risk, make sure they're Class A, similar to your roofs, and installation being important to maintain those as well, make sure not much debris on them. Exterior walls, similar, fire resistant or non-combustible. Cladding is important. Think fiber cement, stucco, metal, not having any gaps, or we use rain screens a lot these days, not allowing embers to get up into that rain screen. So similar, using the mesh. And you can see some examples of vinyl in the top right, melting away, and fiber cement in our similar testing, internal testing, that is pretty resistant. And then for some options to make those truly, wildfire resistant wall assemblies, similar in other architectural assemblies, using gypsum is a good approach to prevent fire from getting to the structure, which is then the biggest loss event. And another one that kind of ties energy efficiency and high performance buildings, using insulation exterior that's non-combustible or fire resistant. And then windows is, I didn't mention it yet, but also one of the biggest opportunities for fire to enter the structure and cause big damage. So so how that happens with vinyl windows, which are on a lot of homes, the vinyl frame will actually melt, and the glass will just fall out of that window. So another is, you have a lot of heat, and glass can only withstand a certain amount of heat. Annealed glass, float glass we call it. So tempered glass, which is more of a safety glass, is more heat resistant. And one way is that we can do that is with double pane, with a single pane. And through some testing, it's important the location of that pane, usually on the interior side. So windows, using a fire resistant frame material, think aluminum, steel, some other ones. And then if you are using vinyl, which is allowed by the code currently, allowing reinforcement or designing those windows so that the glass doesn't actually fall out. And similar idea for skylights. Looking at doors, so similar non-combustible doors, and then looking at the details around those doors, not allowing embers to get in. So using weather strippings and other non-combustible styles and trims and flashings. And then looking beyond assemblies to the actual details. So great, we have all these nice fire resistant assemblies, but it's always the details in between them that can be challenging and vulnerable. So yeah, starting with wildfires and assemblies, and then looking at all those little interfaces. And as a building enclosure consultant, and that we always look at the control layers, thinking of an air barrier or a water resistive barrier, trying to be a consistent line, continuous around your building. So we really look at that as the next kind of control layer, being wildfire resistive barrier. So can you draw a line without picking up the pen off of the paper around your building and all your details through the wildfire resistant construction or barrier? And what is that assembly, what is that material, and how are all those things coming together? It's super important to reducing the vulnerability. And then bring this together, some details. So we worked on a guide with Rockwool, and we've done some other internal guides to help pass this information along. So these are all the assemblies based on different codes, walls, foundations, gutters. You can see here glazing. It's really wrapping up all these lessons learned into guidance to help push the industry forward. And then we have some details in there that point out specific materials and various things to not only provide wildfire resistance but energy efficiency and good building enclosure practices. Similar for windows. And then finally, kind of moving into climate mitigation. So how do we stop this from happening in the future? It comes down to climate change and greenhouse gases. And one opportunity, maybe as we're rebuilding is looking at fuel switching. So you can see on the left here, the various emissions of various fuels, coal, natural gas, petroleum. You see it's high emitting compared to renewable energies, hydro, nuclear, solar, wind, being a huge opportunity to reduce greenhouse gas emissions. You can see just locally here where I'm at in Los Angeles, LADWP has, and the grid, Southern California Edison has switched from, various natural gas, coal to more electric and renewable energies. So you can see the grid greenhouse gas emissions much lower than the rest of the US. And that provides an opportunity to switch, as you build a home, if your grid is very green or use less combustibles, by switching to electric, say appliances or heating and cooling systems, or even looking at vehicles, there's huge opportunities to reduce greenhouse gas emissions and hopefully slow climate change by using electric as opposed to gas. So you can see this is an example from a hospital we worked on. Energy use, reducing energy use as much as we can with high performance enclosures, but then fuel switching, you can see on the right is, from that baseline with code minimum and combustible natural gas, say for fuel, switching to high performance and electrification up to 80% operational greenhouse gas emissions, which is massive over the long term. And then a bunch of resources. There's a bunch of good things out there, not only from RDH and other folks, but a lot of research happening, especially these days with all the recurring events. So I think we'll post these at the end on the website. And I'm going to stop sharing and pass it on.
All right. Let's get started. Hi, everyone. I'm Allie Keenan. I'm a licensed architect here in Los Angeles, and today I'll be talking about healthy materials for fire and climate resiliency. As an aftermath of the January 2025 Los Angeles fires, we've seen dangerous air quality, benzene contaminating the water supply, lead and arsenic in the soil, heavy metals in the ocean. 5 months later, and we're still finding new levels of pollutants. These chemicals put us at risk of cancer, hormone disruption, nervous system disorders, reproductive challenges, infertility issues, and other life-threatening diseases. There are also many unknown lasting consequences and questions. Will kids ever be able to safely play in their own backyards again? These toxic chemicals are coming from our buildings. When I look at this photo, I see the emotional trauma of loss, but I also see the amount of waste. Buildings and the materials that make them deserve a longer life expectancy. The construction industry is one of the most significant contributors to climate change. It's the world's largest consumer of resources and raw materials. It's also responsible for 30 to 40% of global CO2 emissions. As this diagram illustrates, most of the materials used in a standard house are based on a linear take, make, waste process. We mine, we drill, we harvest, over and over and over again. Only a small portion of materials are from renewable resources. Then we use tens of thousands of tons of hazardous chemicals to turn these resources into building products each year. Chemicals that are linked to negative impacts on human health, a decline in biodiversity, an increase in greenhouse gases, and many other environmental disasters. An alarming amount of these materials then end up in landfills each year, not able to be reused or recycled. To me, when we talk about fire resiliency, we can't leave climate resiliency out of the conversation. Climate change is happening, and there's no stopping or solving the crisis at this point. We do have the tools to minimize the damage, mitigate the effects, and stop it from getting worse. But it will take collective action and an industry shift. We also have a nationwide health crisis. Whether people know it or not, they are getting sick from their buildings. That being said, fire resilience requires a holistic approach. There isn't one solution to make a building fire resilient, nor will anything ever be 100% fireproof. How can we make less of an impact to our communities, to our planet, to our health? How can we reduce the amount of environmental pollutants, plastics, foams, forever chemicals? How can we lessen the impact to our planet's resources, raw materials, and labor force? We need to steer the rebuilding conversation this way, to more sustainable, more natural, and healthier building techniques and materials. This typology is truly high-performance design. What is a healthy home? Healthy for the home's occupants, healthy for the home's builders, healthy for the material manufacturers and surrounding communities, healthy for the planet. At this point in time, this concept still takes an immense amount of convincing to both homeowners and contractors. I hope to give you some tools to evaluate your decisions as design and building professionals. Once we get more momentum, we can build more purchasing power to help stabilize the pricing and supply chain of these products and to grow the knowledge base for labor and installation. We, as building and design professionals, have a lot of power. Americans spend approximately 90% of their time indoors. The air inside our homes is 2 to 5 times more polluted than the air outside. Chemicals and materials are not static. Volatilization, leaching, oxidation, and degradation are some of the processes that release substances from materials into the surrounding environment. On a typical day, you are then exposed to these chemicals through inhalation, ingestion, and dermal absorption. Now fire is thrown into the mix, creating toxic ash, dust, and new chemical byproducts called dioxins that contaminate surfaces, air, water, and soil. Products we use every day can contain chemicals that may be harming our health. Many of these chemicals of concern can be grouped into 6 classes, each containing similar substances. PFAS, antimicrobials, flame retardants, bisphenols and phthalates, some solvents, and certain metals. Looking at PFAS as an example, you'll see how many common household items and building materials contain them. PFAS are forever chemicals, meaning they do not break down in the environment. The use of flame retardant in furniture, mattresses, children's products, electronics, and building materials provide limited fire safety benefit. Research shows that they often delay ignition only a few seconds and can make a fire more toxic. Even flame retardants developed as eco-friendly alternatives could be more harmful than expected. There's a common pattern in industrial chemistry to replace banned chemicals with similar yet not well understood compounds. Often the substitute compound turns out to be equally problematic. Smoke detectors and sprinkler systems are more effective to prevent a house fire with an interior ignition source. Sheep's wool is a natural alternative to chemical flame retardants found in upholstery and mattresses. There are bio-based materials that are inherently fire resistant for exterior rated assemblies and building insulation. In the haste of rebuilding, I've heard a lot of people throwing around foam panels, concrete bunkers, Trex siding as a solution to fire resistance. Fire resiliency doesn't need to be concrete or foam or plastic. We can turn to plant-based and earth-based low-carbon materials. We can incorporate these into fire-resilient assemblies. Earthen building is the world's oldest high-performance and sustainable construction technology. Materials that originate from ecological sources combined with current technology can produce durable, high-performing, and regenerative building products. Many earthen and bio-based building techniques are inherently fire-resistant. They have low embodied energy, small carbon footprints. They naturally sequester and store carbon from the atmosphere. They can replace plastics and other fossil fuel-based products. Ideally, they biodegrade at the end of their useful life and benefit the ecosystems. Earthen and bio-based materials lead to an entirely new wall assembly, which includes the elimination of several material layers found in a typical wall section. Looking at hemp lime specifically, you can see in the right-hand column that there are only 6 materials needed for the wall. Because of its inherent qualities, it acts as paint, drywall, insulation, vapor barrier, and metal lath. Compare that to a traditional wood clapboard assembly that uses double the materials. This simplification reduces the complexity of a wall, reduces cost, and significantly reduces the amount of embodied carbon. Hemp lime is naturally flame retardant, which eliminates the need for added flame retardant chemicals. The material's vapor permeable and its humidity regulation can just drastically reduce mold and bacteria growth, eliminating the need for added antimicrobials. It's also naturally resistant to pests, eliminating the need for pesticides. Hemp and lime products are naturally biodegradable and can be fully recycled to support a zero-waste economy. Let's take a look at a more conventional construction assembly. When considering high-performance design and fire-resilient design, even separately, unvented roof assemblies are the answer. Continuous thermal bridge-free insulation is the best insulation. It provides predictability and protection. It pushes the condensation plane to the exterior of the roof, mitigating moisture and mold issues. It eliminates eave and roof vents, which are common entry points for embers during fires. Continuous insulation also acts as a fire-resistant layer of the assembly. As you can see from this diagram, the typical unvented roof details will include XPS, EPS, or polyiso rigid foam, or closed-cell spray foam insulation. Foam insulations contain toxic flame retardants, and spray foam contains asthma-causing isocyanates. These products are also petroleum-based and can have significant impacts on communities throughout the manufacturing process. So how can we make this system healthier? When evaluating these conventional assemblies, the website Informed is my first stop. For each building component, it lists the different material choices and rates them based on health impact. Here you can see that rigid foam boards and spray foam are all in the red. Looking to the green zone, we find alternative insulation boards that work with this assembly: expanded cork, wood fiber, and mineral stone wool. Next, I look at the construction material pyramid to compare and visualize the environmental impacts associated with the production of different material categories. Note that healthier material options with biogenic properties tend to have lower embodied carbon and are at the bottom of the pyramid, compared to synthetic chemicals and energy-intensive metals at the top. Using the same color coding as the Informed chart, I've highlighted our insulation choices. Wood fiber and expanded cork are both carbon negative. Stone wool is still low on the pyramid and performs better than XPS foam. Using these tools, we found 3 healthy home alternatives for an unvented roof assembly. Cork and wood fiber are renewable resources with negative carbon emissions, no environmental pollution or damage to health. Both have Class B fire resistance. They're workable without skin, itch, or irritation. At the end of the life, they're recyclable. Cork is even biodegradable. Nearly perfect on paper, historically they have been harder to source within the US market and have a higher upfront price. Let's change that. Stone wool is a little less perfect, but it is more readily available and cost-effective option that still aligns with a healthy home. Companies like 475, High Performance Building Supply, Small Planet Supply, and Rockwool are great resources with open source assembly details using these alternative materials. Looking at the Informed website again, let's run through a few other fire-resilient healthy home options. Our windows are the weakest point in our building assembly, both from a thermal perspective and in a wildfire event. We see here that vinyl and PVC windows are in the red zone for health impact. These windows frames will also melt in the high heat of a fire. Instead, we should be using thermally broken aluminum or aluminum-clad wood windows with dual pane tempered glazing. Aluminum has a very high embodied carbon, but it is infinitely recyclable. Anodization is a relatively low hazard aluminum finish option. Watch out for frames that have chromate pretreatment or PFAS-based color coatings, which are ranked red in this guidance. We may have phased out lead in our paint, but it still contains acrylic latex. Acrylic latex paint off-gases volatile organic compounds, or VOCs, and forever chemicals, which impact interior air quality. It generates significant microplastic pollution, and it needs to be responsibly disposed as hazardous waste. On the other hand, lime and mineral paints have no VOCs, no forever chemicals, and no disposal limitations. Not on this list, I also specify linseed oil paint for wood and metal applications. Another great resource that I can't fail to mention is the Healthy Materials Lab from Parsons School of Design. They offer an extensive materials database geared towards healthy materials, as well as material teaching guides and coursework. This is where I got my start as an advocate. All it takes is some conscious decision-making, and we can move away from high-carbon, toxic materials sitting in a landfill polluting for their entire life cycle to negative carbon materials that are chemical-free and compostable. We can't deplete the planet of her resources and then expect that she will be kind in return. We can't use toxic materials and expect not to get cancer. We can't build the exact same way as before and expect to have better environmental quality during and after a fire event. Let's meet this challenge with optimism because we actually do have actionable tools to help mitigate this crisis. Thank you. I'll pass it on to Ben.
Thanks, Allie. Okay, so let's see. Well, first, thanks to Clayton and Allie for their presentations. I think what you all have just heard represents the best advice that you're going to get about how to appropriately design resilient, healthy, and efficient buildings within the parameters of today's regulatory environment and maybe more importantly, construction ecosystem. So if you're planning on a new construction project or a rebuild in a fire-prone area, those are the techniques that you need to use. But I'm going to spend a little time now talking about what's next and the barriers and opportunities to doing the right thing for the next time this happens, because we know it inevitably will. And I'll just say right at the beginning that approved technologies that are available today are insufficient. The Eaton and Palisades fires are a catastrophe that we made ourselves, and the consequences of how we practice and regulate construction are to blame. It's the result of infrastructural neglect, inappropriate building practices, and human-caused climate change. And there's increasingly a recognition that we have to do things differently and a growing movement to explore the use of regionally produced, fire-resistant, carbon beneficial materials and systems like earth and straw is underway. But the issues around them are complex and vexing. First, California is under various mandates to reduce carbon emissions and embodied carbon from building materials. And I'll talk a lot about California because I think we are the canary in the carbon mine in this case. But and what's going on here, I think, is representative of what's going on in a lot of other Western states. We know that fires are increasing both in frequency and intensity due to human-caused climate change. The building code in many jurisdictions mandates the use of specific materials in fire-prone areas. Those materials are almost entirely non-regional and carbon intensive. And codes to allow locally sourced carbon beneficial fire resistant building materials are not recognized in California as well as many other states. And while we're all having a lot of discussions about home hardening to increase the resistance that wood frame construction has to external fire sources, these code provisions have been part of the California Code here since 2008. And while well-meaning, the solution is also part of the problem as it's currently presented. Here you see a graph showing carbon emissions associated with typical exterior finishes. And here in green, you see the ones that are endorsed by CBC 7A for use in wildland urban interface areas. And for the most part, the ones that CBC 7A asks us to use also have the highest associated carbon emissions. Another way of saying that is that the precise materials that the building codes are prescribing to help protect structures from wildfires are contributing to their increased frequency and intensity. And earth, which we see here on the far right, is a great alternative. Straw and hemp, not shown here, are maybe even better. They might be carbon beneficial, depending on how you address fertilizers and end-of-life issues. But what are the realities of their use? And why are they unlikely to be used in the rebuilding of Altadena and the Palisades? The issue is really that the building code is scoped in a very particular way around particular concerns. And here I'm showing you an excerpt of section 1.1.2 of the California Building Code, very similar to what's in the International Building Code. And what it cares about are a handful of specific issues that are pretty well known to us: fire life safety, egress, durability, light, space conditioning, to some extent, water use, energy efficiency. But they're not at all concerned about other things that we're finding of urgent concern in the wake of these fires. I'll highlight just a few of them, but it's a big list. Toxicity, embodied carbon, climate impact, end-of-life consequences for materials when the buildings are no longer used. These are not considered as important by the building code. And so we know that's not sufficient, but we have to rebuild with the codes that we have. So what's currently possible? Here in California, straw bale is the easiest. We have this California Residential Code Appendix BJ, which was adopted throughout the state as a result of an assembly bill due to the work of a bunch of rice farmers, interestingly enough. Interior earth and plasters. Interior finishes are relatively lightly regulated and easy to use. Exterior lime plasters are allowed by the California Residential Code and IRC R703. That list of code endorsed materials is a pretty short one. This is like where we're getting to the edges of what can be done easily. And the question is really like, are we stuck with only those things that are explicitly permitted by the building code? No. Any code that is based on the IBC or IRC, California included, has this provision 1.2.3 in California for alternative materials. And what this says is that you can use any material or assembly that you can show as equivalent to other materials in the code. That's for flammability, durability, structural performance, all that kind of stuff. The bad news, in many jurisdictions, that's enough. LA County and the city of Los Angeles are unique I would say, maybe not perfectly unique among California jurisdictions, in that they require third-party evaluations intended for manufacturers of what are mostly mass-produced products in order to demonstrate compliance. So for earthen and bio-based materials that are locally sourced, more variable in their properties, these testing requirements can be effectively impassable hurdles. So that said, what isn't specifically in adopted codes, but still possible with some grit? Light straw clay in a lot of jurisdictions. This one is relatively easy to use. There's an appendix BI in the International Residential Code that guides its appropriate use. Good luck, City of Los Angeles or County of Los Angeles. I think they appear not favorable towards the use of these materials. Hemp lime, hempcrete, same thing. There's a appendix in the IRC, makes it available. Good option in other jurisdictions, not so much City or County of Los Angeles. Cob, monolithic adobe. This is a great one in non-seismic areas. It can be used with restrictions in higher seismic risk areas. Not currently a viable option in the City or County of Los Angeles unless things change. And then, what's in the code but hard to use? This is sort of a different category. Adobe brick is in these. It's in the International Building Code. It's in the California Building Code. The provisions around it are challenging because building codes are mostly authored by trade associations and fund lobbyists. That hasn't been available for a lot of earthen and bio-based materials that don't have huge profit incentives to impel lobbying by manufacturers. Tough one to do in City and County of Los Angeles. We have been successful in San Bernardino County. Things that are adjacent to the code, so not explicitly included. Compressed earth block is among these. Can most of the time be designed according to those same Adobe provisions in many jurisdictions. You saw this one coming. City and County of Los Angeles, super hard. Super Adobe. This is a material that they actually went through the CalEarth folks went through a process of getting an evaluation of this by ICCES. Can be used in non-seismic areas, very difficult to use in seismic in areas of higher seismic risk. And here's a quick rundown. Like these appendices, super important if you're a designer and want to kind of stretch the limits to look at these, talk to your local building official about whether they'll allow them. So you can see lots of red nose for the state of California for statewide adoption. It doesn't mean that you can't use them under that alternative means and methods request. So keep an eye on that if you're interested. And then zooming in on Southern California, this is what it looks like at the local adoption level. Again, not great news. We are not a region that, statements to the contrary notwithstanding, is very friendly towards sustainable materials. We'll talk about that, I think, in the discussion. How do we gain better codes? It's often easier to change the building code for the entire United States than to obtain a permit for a single earthen or bio-based building in California. That's true. I've done both. For minor improvements, operating at a national scale is thus probably the best approach. But for significant changes, the type that we need to do now in the wake of these fires, there may be no substitute for legislative action. I don't think we can rely on the federal government at the moment to help us do the right thing. Your local politicians and assembly members, representatives are the ones that may be able to make these changes. The straw bale code that is now available nationwide was only created because of lobbying to California State Assembly members. The Building Standards Commission would never have allowed it on their own. They were very unhappy when they were told that they had to create regulations allowing it. So anyhow, that's me. That's what I've got to share. Looking forward to the discussion. Thanks, everybody.
Thank you so much, everyone. These have been truly exciting and interesting presentations. I've been monitoring the Q&A, and I tried to kind of group some common themes. I think so. I'll kind of maybe list a couple of questions under the theme, and if there are any that any of you feel like answering, please weigh in. The first kind of grouping I was kind of seeing what was centered around kind of cost and effectiveness, and how code and policy can start to respond to this. So a couple of questions under that. One is, can you speak about the incremental cost to building resilient homes, to fire hardening and defensible space? Are there any resources or data you can point to that touch on that cost and effectiveness? And in a similar vein, are there any kind of elements of the code, of tax incentives or other policies that are acting as barriers to implementing some of these cost-effective strategies that we have talked about today? Are there gaps in these policies, and what are kind of the biggest elements that are going to have to change to move forward some of these solutions?
Yeah, I can talk about the incremental cost. There's been various studies done. AIA has done one. We've done some internal, actual cost estimates for archetype homes, and looking at code minimum requirements to what it takes to get to a fire resistant state is maybe a 2% incremental cost above base code design, which we all know what base code means. Bare minimum. And if you look at on the backside, the cost of mitigation, for every $1 mitigation spent, say in that 2% extra, think of a total loss situation where you have to rebuild from ground up. It's maybe $1 for mitigation, every $4 of rebuilding. So it's all kind of a reference point of what what value are we bringing. It's hopefully that home survives and don't have to go through the rebuilding effort.
Yeah, and just to further that point more, I think we also have to think a little bit at the bigger picture and look at the cost to our health and the cost to our planet. And it might be more expensive up front, but down the line, if you're footing the bills to high medical bills or our planet is crumbling, it's worth that investment up front. And there's also a lot of great rebates out there that look at a lot of electrified systems. So for heat pump, heating and cooling systems, water heating systems, drying and dryers, clothes dryers to look for. And also through LADWP, you can do a landscape rebate, and they actually do reimburse you a good amount of money to take out your grass and replace it with native landscaping.
Yeah, and on that landscape piece, there's a lot, the existing building stock is a huge contributor to the risk, and simple things like landscaping you might be able to do yourself or at low cost. But then looking at existing building retrofit to provide wildfire resistant is a thing as well.
Thanks. And maybe, Ben, as you were kind of touching on more of the code piece so thoroughly, I'm wondering if there were any, I guess, gaps or big code changes that you would identify to kind of promote some of these.
Yeah, well, I mean, there's a ton of work to be done, right? And the issue with a lot of these materials is that although we know that they work empirically, like earth and construction, we only have like 8 to 10,000 years of experience with it, right? So we have a pretty good sense of what we can expect it to do well and not do well. But for all of these materials, whether old or new, the challenge is that we need to, although they might be alternative, they're not alternative to the same standards of evaluation that other materials, conventional materials have, right? And what the gap often is that in this country, although the materials are pervasive, they're low cost, these are actually barriers to their use because we don't have an industry that is rich enough to do the research to prove out how they perform, the ASTM tests, which are quite costly, and all that kind of stuff. So I think, what I would love to see in an alternate version of the country that we live in right now is that is an investment in public benefit research around this stuff, both at the federal, state, but also local level, to reduce some of these barriers. Because when we're speaking to local building officials, they're saying their hands are tied, like they have no ability to approve this stuff, even if they want to. At the same time, these same jurisdictions, the county is investing nothing in solving the problem. The state is investing nothing in solving the problem. It's entirely reliant on private industry. And I think the analogy here is if we found a plant growing in our backyard that solved some, pervasive chronic illness, we would find a way to do the FDA testing and trials that it would take to allow us to use it. I'm not sure why that hasn't been the case, why our elected officials haven't seen that same line of thinking applying to how we build buildings.
Thanks. And I wanted to, I know we're a little short on time, so I think I'll leave time for maybe 2 more questions. One, I was seeing a couple around the topic of passive house. One was saying it looks like passive house with non-combustible materials would minimize fire risk. Is that an accurate assessment? Another was asking who is actually using passive house design integrated with magnesium oxide structural insulated panels, and if not, why not, when it's readily available and a proven way of being non-combustible and smoke-free? So if anyone has any answers.
I can talk on passive house. We do a lot of passive house. Yeah, and passive house is not by itself, fire resistant. When you think of passive house, it's a lot of exterior insulation most of the time. So like Ali mentioned, rock wool is a good exterior insulation that not only provides that fire barrier, but gets us to passive house level energy efficiency. So with the right materials and the right fire resistant, assemblies, totally. And it's a great kind of dual purpose guideline, being passive house. And then the magnesium oxide sheathing. Yeah, there's been a lot of history on that. There's some issues with moisture, relative humidity, and crying, they'll call it. So there's been some hurdles for the industry to get over, and I think there's more and more research and development happening in that space, and it is inherently fire resistant and insulated. So definitely, kind of climate by climate basis can be an opportunity maybe, but yeah, there's other materials as well.
Thanks. And I guess maybe one more question kind of to close us out is also a multi-tiered question. I see a comment in here about kind of thinking about the interplay of fire resistant strategies with consideration of other natural hazards. I'm wondering if you have any comment on kind of what are those strategies that play well with each other and what might come in contrast. Maybe I'll stop there and see if there are any. As we're kind of thinking about, there was a note here about earthquakes. I think there's also, other climate impacts we want to be thinking about, like the urban heat island or water scarcity. Are there any strategies that kind of like that could be mutually beneficial?
Yeah, I think, in terms of, high, demand reduction and looking at, highly insulated or energy efficient building enclosures, not only minimize the amount of energy use in normal times, but say if we have a power outage or like the resiliency type thing, where those heating or cooling systems may not work in a building, it is limiting the amount of heat and or cold depending where you're at in the country. It does get into that enclosure. So yeah, passive house and energy efficient provides that resiliency as well. It's fire resistance if it's done right.
Yeah, for water scarcity, I definitely recommend looking at rainwater harvesting and gray water reuse. Rainwater harvesting could be used both for firefighting, if it's stored in metal tanks to supply exterior sprinklers. It can also help with irrigating landscape. Irrigation to landscape, we saw does help protect buildings from fire and typically will withstand the high heat elements of fire. Another really easy system to employ is a laundry to landscape gray water system. I installed my own at my own house after one day workshop. And basically that's reusing your laundry water and redirecting it to your landscape. So again, keeping your landscape green. Another great strategy for water scarcity is looking towards native plants. Native plants don't really even need to be irrigated. When you plant them, they need to be irrigated for a couple months, and then they don't rely on any sort of drip irrigation or supplemental water other than natural rainwater. So again, looking at saving our resources, planting native plants, also helping the ecosystem and the biodiversity.
Great, thank you. Maybe I'll close us out with a quick round robin, kind of focused on recovery. So as you know, there are communities that are looking to recover from past wildfire events. Maybe in just a couple words, what do you think the priorities should be in these rebuilding efforts, either from kind of a mandatory policy perspective, a building strategy perspective, or kind of a voluntary incentive-based perspective? What should those priorities be moving forward?
Yeah, I'll just say, as terrible as tragedy was, it's a opportunity to rebuild in a way that's hopefully mitigating future climate change, but also providing resiliency through for fire, energy efficiency and that. So it's really passing and getting the knowledge out that there are ways to do this, and that we should be focusing on how we can use that to set us up for the future.
Right. Yeah, I'll amplify that. I mean, I think that I can't blame anyone, like anyone who's been affected by these fires or any fire, their highest priority is restoring their home and their community, right? And a lot of the macro stuff that we know might be the best practices, which is like changing land use planning, changing the building codes. These are things that take so long. It's not practical to implement them in the wake of these fires. But we absolutely have to start thinking ahead, which, if we miss these opportunities, and we have regularly like, and predictably every time that it's happened, we are just going to keep rehearsing the same catastrophes over and over again. And that would be an even greater tragedy than the one that we've already suffered.
Also community resilience, you know, we're all in this together. So I think we do need to talk to our neighbors, talk to our communities, and make sure everyone is thinking about these resilient strategies. Also, you don't need to be in a fire zone to think about healthy materials and materials with high embodied carbon. So I think it's important for everyone.
Yeah, that's a great note to end on, I think. Thank you all for the time you've put into these presentations. I personally learned a lot from it. And thank you everyone who has attended. Again, these will be posted online, the slides and the recording, so you can all refer to all the resources that were referenced in the slides. And yes, have a great rest of your day.
Thanks,
Thanks,
everyone.
everyone.
Thanks, everyone.